about the wave equation. All right, so let's talk wave equation. Wave equation. So first we're going to recap a few things that we've already talked about. The first is the concept of period. Period. Okay? Period simply meaning a length of time. Okay? The length of time. We have periods in the school day, periods in a hockey game. Lots of things refer to lengths of time and are referred to in terms of periods. Okay? The second thing is frequency. And this is how many times something repeats. Every second. Okay? So period is measured in terms of seconds. Frequency is measured in terms of inverse seconds. Okay, in other words, per second. So what that means is by looking at these units, a conclusion you should come to is that one is the inverse of the other, and we did cover that yesterday. So frequency F is 1 over T, and therefore T is equal to 1 over F. So in terms of waves, okay, if we draw ourselves a little wave here, okay, as that wave moves along, the time it takes for a particle in the wave to move up, down, and then back up, if we're, say, only looking at this spot on the wave, okay, so the time that takes is equal to period. Okay, we can look at frequency in a similar way. If we set our stopwatch and we look at how many oscillations of the wave we have in a second, okay, that will give us frequency. But with a traveling wave, like we've been talking about, so if I, take my slinky and I'm going to draw the famous hand, kind of like I drew yesterday. Yeah, there it is again. Look at that. Okay, and I oscillate this such that the waves move along from their starting position. What I could do is I could put an imaginary wall here, right? And I could say, okay, these waves are traveling towards me. And every time a wave crest passes this point, I count that as, one wave. So what I can then do is I can say, all right, I'll time it, and I'll see how many wave crests hit my imaginary line every second. And that will give me my frequency. Okay? From that, I could go back and calculate my period. So velocity is tied to frequency. Let's just think about how that might be true. Okay? So what we have here, the distance between two crests, we gave that a name yesterday, didn't we? What do we call that? Distance between two equal points in a wave. That is the wavelength. Okay? So these are crests. Why? Because they're on the high side. These are troughs. Why? Because they're on the low side. This is wavelength, and it's symbolized by that Greek letter lambda. I'm not really drawing it that well. It's kind of like this thing. All right? If you're into like half-life, it also has to do with half-life. This is an eyeball, and it's the universal symbol for eyeball. So if we think about this, if we keep the same wavelength, right? Let's say we fix the wavelength, but we increase the velocity of the waves. What's that going to do to the frequency? If we keep the same wavelength but make the waves move faster, what would happen to frequency? Right. A higher velocity with a set wavelength would cause a higher frequency, right? Waves would hit more often. Okay? Let's think of another thing here. Let's say we fix velocity, right? The velocity of a wave, and we haven't discussed this yet, but we'll put it into notes in a minute. The velocity of a wave depends on medium. Okay, so velocity is dependent on the medium. And what we mean by that is if we change the medium, we'll end up changing the velocity of the wave. And we saw this in a little example, okay? If you take a spring, like a big slinky, and you loosely hold it at 2 points, the wave will move quite slowly. But if you tighten up the slinky, you're changing the medium, you're increasing the tension, and if you do that, the waves will move faster, okay? We haven't really like changed the medium per se, we haven't changed the material that's made out of, but we've changed a property of it. We've increased tension, and that will increase the speed at which a wave travels through it. So velocity is dependent on medium. So in this case, let's imagine that this is a spring, and we have just simply increased its tension. We keep the same wavelength, we increase tension, okay, that will make the wave travel faster and give us a higher frequency, okay? But let's say we fix velocity, okay, and we put a longer wavelength. We fix velocity and we make the wavelength longer. What would that do to frequency? Right, so increasing wavelength lowers frequency, okay? So we kind of have a relationship between wavelength, velocity, and frequency. Let's see if we can write some like little helpers to say that. We could say velocity is proportional to frequency, right? You raise one, you raise the other, keeping all other things equal, right? You have to make sure you say that. Keeping wavelength constant, right? That should make sense to you, right? We just said, right, if we make the wave go faster, the frequency will go up if we hold wavelength constant. If we hold velocity constant, then increasing wavelength decreases frequency, right? Decreases frequency. So if an increase in one thing causes a decrease in something else, what kind of relationship do we say that is? So where the increase in one value causes a decrease in another, we can call that an inverse relationship, okay? And that's keeping velocity constant. So we're going to keep that in mind because what we're going to come up with is an equation that sort of states this out for us. But before we do that, okay, I'm going to do a little analogy for you, okay? Let's imagine some train cars. I'm going to draw a little train. Okay, here's my train. Okay, a lot of criticism about this end of the train. I am so sorry, okay? The point is this, though. A train pulls box cars, doesn't it? Okay, it pulls box cars along. Let's say we know something about these box cars, okay? Let's say that we know each box car is 10 meters long. Okay, 10 meters long. And let's say that we have box cars passing our eye, or let's say we draw like a little line here. Oh, we'll draw it here. Okay, and we're train spotting. So we've got our eye on the train here. There's my eye. Okay, there's the eyelashes. And I am watching train cars go by. Okay, that's what I'm doing. Now let's say I have a little stopwatch with me. Stopwatch. Okay. Ticka, 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 ticka. And I am counting train cars. Let's say I get like 5 cars every, I don't know, 10 seconds. 5 cars go by every 10 seconds. Okay? First of all, what is the frequency of cars going by? How would I calculate that? Remember, my unit for frequency is the per second, right? So would I not just say 5 cars go by every 10 seconds? So half a car would go by every second? I guess what we're saying is we have a half hertz frequency for the train, right? 5 cars every 10 seconds means half a car every second. Do we all agree with that? Yeah? Sweet deal. Okay. So if half a car goes by every second, can we figure out what the overall velocity of the train must be? how fast is this train going? Is there a way to do it? Well, don't I know how long each car is? It's 10 meters. So if half of 10 meters goes by every second, how many meters go by every second? 5 meters per second. So I'm saying I get 10 meters going by every half second. Multiply it through, must be 5 meters per second. Okay? So this little illustration here is just meant to show you that the wave equation isn't hard to understand. I mean, you can come up with it on your own. This is a stand-in for wavelength, right? That's a stand-in for wavelength. This information is enough to figure out the frequency, okay? And this is our unknown value. What's the velocity of our train? So if we just convert all of our values to, instead of being about train cars, about a wave moving by, we can get this. V is equal to the frequency times the wavelength. Or, as we normally write it, just V equals F lambda. That's exactly what we did. Remember, frequency, how many cars go by per second, times lambda, the length of each car, gives us the overall velocity of the train, right? 5 meters per second, okay? So this is what we said before, right? And I just want to note, is this equation, sensibly follow those rules. So what we're going to do is we're just going to quickly rearrange this formula, right? So let's solve for lambda. Well, lambda is lambda times frequency. So you see a little algebra, divide f off both sides, and we get lambda is equal to v over f. If this stays constant, look, we said there's a proportionality here that we would be equal, that lambda would be proportional to something over f. Well, we had 1 as our stand-in, but it's equal to the inverse over f if we know what v is, right? So we're good there, no problem. And if we just leave it in its normal original place, we look and we see, okay, as v goes up, f goes up if we hold lambda constant, okay? So we do obey our sort of understanding of the wave equation. We actually write it out. And that is really all there is to understanding the wave equation.